Testing, testing. 1, 2, 3. Good afternoon, Fancy Meat Computers. How is it going this lovely afternoon? Hopefully your day has been going well. Yep. I see we only have 14 people today. That's 17. Ah, there we go. That's slightly more than 14. You know, it's just kind of interesting to have the traditional end of semester drop off in viewership right at the beginning, like within the first week, you know? Because, you know, this class is supposed to have, what, like 70 people in it? Anyway, that's okay. The few, the proud, the 17, 18. Yes. So, oh my goodness. Oh. Ba-doop. Gotta keep that one open. Okay. So, there we go. There we go. There we go. What is that? Hand sanitizer? Almost forgot that you were using different links today. Yes! Okay, cool. Hopefully people remind our yeah. I mean, I did post the links. The link is right there. No excuses. Come on. Come on, folks. Anyway. Right. So, yeah. Welcome to 3MI3. We're going to get into some of the meat and potatoes of the course today. Or at least, we're going to talk about the preliminaries to the meat and potatoes of the course today. So, buckle up, because we're going to do some math. Yep. Oh, 28. Okay. Do you guys all have a class before this or something? Anyway. So, last time, we were going through topic 1, which is the introduction to the course, and we had managed to polish that off. So, it therefore follows that we shall begin with topic 2, mathematical preliminaries. We're going to talk about sets, relations, and functions, ordered sets, and proofs and induction. So, wait! This is a math class? What? Before we get started with the course proper, it will be useful to review some of the math we'll need. If you are unfamiliar with some of the concepts in this lecture, or you don't feel you know the material very well, you are strongly encouraged to study these topics in preparation for the rest of this course. This course is pretty mathy, so a firm foundation is essential. This topic is going to be primarily, hopefully, review. I'm going to rely on you guys to tell me if we talk about anything during this topic that you guys haven't seen before. I think that you should have seen the vast majority of the stuff that we're going to be talking about. So, you know. A math class is keeping you, huh? So anyway. So yeah, this course has as a prerequisite both 2LC3 and 2FA3, so, you know, hypothetically, you should have passed those courses in order to be able to take this one. So there you go. So, let's talk about sets, relations, and functions. Sets. We're going to build it right from the ground up. So, we will use standard notation for sets. Part of the reason for going through this stuff also is depending on which class and who the professor is and what textbook they're using, the conventions that we'll be using are like very slightly different from offering to offering. You know, it's like, you know, one professor might use this symbol, another professor might use that symbol. Generally speaking, there should be like a reasonable degree of accord between all of the professors and all of the various symbols that they use. But, you know, it is useful to review stuff in light of the syntax for math that we'll be using in this particular class. So, the elements of a set are delimited by curly braces. So, the natural numbers are 0, 1, 2, 3, 4, etc. The natural numbers are going to be important as time goes on. The above is the set of natural numbers. The empty set is denoted by a 0 with a slash through it. So that's the empty set. If you remember, some of the properties of the empty set are that the empty set is a subset of every set, and that it is a set that contains nothing, hence empty set. Set comprehensions are written as curly braces, x in S, phi S. This is interpreted as the collection of all elements of S satisfying the predicate phi S. In lecture, you will often hear me pronounce the bar here as such that. So, all x in S such that phi. Right? Making sense so far? Can I get a thumbs up? hopefully. So in addition to sort of the nominal manner in which sets are constructed, we have a number of operators that, again, important to realize that these all are things that exist. So, set membership is the backwards E thing. Union is this cup. Good, thank you. Intersection is an upside down cup. Difference is going to be a slash this semester. Sometimes difference is the minus sign, but we're going to do set difference with a backslash. Excellent. Set size will be denoted by the two vertical bars which normally denote magnitude. So set magnitude is using the two vertical bars. Subset is, cup to the left. Superset is cup to the right with the lines underneath. So that, of course, means that the set S could be the same as the set T. Ha! Moo. So the set S could be the same as the set T, but it's at least, it's at most as big as T. In the case of a superset, S is at most as small as T in terms of its actual elements, not in terms of size. This is to contrast with the strict subset, which has the line removed. So we are removing the idea of equality from the subset and the superset. That means that S is at least, S is at most one element less than T. And in the case of superset, S is at least one element larger than T. Normally, when we talk about subset-superset relations, we're not going to work with strict subsets so much as regular ones. But, it is what it is. We also have the power set of S. So, can somebody in the chat tell me what the power set is? And I'll continue on to the logical operators. Our logical operators are, of course, existential and universal quantification, negation, or, and, another way of saying that is disjunction and conjunction, implication, if and only if, proving, modeling, and, of course, true and false. Additionally, this was like a longer description, so it didn't fit inside of my nice little chart here. S times S. Yes. The set of all possible permutations of the set S. The set of all sets. Not quite. It's the set of all possible subsets. So, if you had... let me see. Yes, thank you. I want something. I just want a scratch pad. Examples. Get it. Yes. So let's say we had the set 1, 2, 3, right? The power set of this is 1, 2, 3, 1, 2, 2, 3, 1, 3, 1, 2, 3, and the empty set. The empty set is, of course, a element. Oh, I need to numlock. There we go. So that's, if S is this, then the power set is that. There we go. Ha! Well, yes, the set of all possible combinations of subsets in S. Yes. So it's the set of all subsets. The set of all subsets is like that's like your minimal and sufficient definition. We also have S times X, which denotes the set of all possible tuples containing one element from S and one element from T. So, that's kind of a tricky one. Well, it's not that tricky, but, you know. So if we have two sets, S and T, right, and this one's 4, 5, 6, then S times T is going to be 1, 4, tuple, 1, 4, you know, 1, 5, etc. on down the line, then 2, 4, 2, 5, 2, 6, 3, 5, 3, 4, 3, 5, 3, 6. So this is going to be important when we bring in relations, because this is like S times T is the set of all possible relations, essentially. Kind of has the same relation to relations that the power set has to subsets. So, let's talk about relations then. An n place... we're up to 42 people. That's good. So you guys do... does S times T include an empty tuple? No. No, it doesn't. Okay, so the analogy breaks down. I'm not sure there is such a thing as an empty tuple. There's an empty set, but I don't think there's an empty tuple. Maybe a tuple between the empty set and another empty set? I don't know. Does order matter? Yes, generally. Yeah. So, does the order matter? 1, 4, and 4, 1. So, yes. Order matters with respect to tuples, unless, like, if order doesn't matter with respect to tuples, then you have a reflexive, or is it reflexive? No, it's symmetric. Then you have a symmetric relation, right? So that's a property of the relation. You should go in assuming that the tuple, the ordering in it matters. Yeah. What if S or T is empty? Then I think you would get an empty... You would get emptiness. I'm pretty sure you would get an empty set of possible tuples. Yeah. So. Okay. So. Moving on to relations. An n-place relation on a collection of sets S1, S2, S3, all the way through Sn is a set containing tuples of elements. A set containing tuples of elements from S1 through Sn. Ignore the of, please. R is a subset of the sets... R is a subset of the set of all such possible tuples. So if you take this multiplication operator and, you know, bang that out for, you know, all of the different sets, kind of in the same way that relational databases will join tables, then you get the set of all possible tuples, and the relation is a subset of that set. Cool. If S1 is an element, if S1 is an element of the set S1, through Sn is an element of the set Sn, we say that these elements are related by R if the tuple that they form is in R, right? So that's a thing to think about with relations. Relations are sets of tuples. The elements that are in the tuples are said to be related by R if they're in R. Cool? So far, so good? Thumbs up, everybody? Hopefully this is all review. So, it really depends. This is one of those definitions that will definitely depend on like what class you're taking, how a predicate is defined. So, in our case, we're going to define a predicate as a one-place relation on a set S. We say that the predicate P is true if an element S in the set S is also in the predicate. So we're going to think of predicates as being a subset of the set. We will often write predicates in the form P of S, just like functions which map S to truth values. So often you'll have, like sometimes you'll have predicates defined as functions that, like functions from the set S to the set true-false, right? In this case, the sort of truth or falsity is implicit in the membership. So, will all elements numbered 1 to n have to be in R? Yes. So just to go quickly back, you need one element from each of these sets to compose the tuple. Bowtie matches the slides. Really? Because it's ducks. I wore my duck. This is my duck bow tie. See? Yeah, I'm wearing ducks today. So, is S1, S2, S4 in R? Okay. The relation has to specify quantity of accepted valid pairs if the pair from S are a list of pairs that make up R. Yes, so yeah. Normally, like we have to generalize. Like the difficulty we're having is generalizing from binary relations, which I think everybody gets intuitively, to like the n-place relation, right? So for it to be an n-place relation, you have to have an element from each of the sets in the tuples that form the relation. It would have to have a tuple of size n. Yeah. Eps from S3. Yeah. Good. Okay. Did I just hit end? Oh, good. That didn't. Okay. Sometimes, in some viewers, when I accidentally hit end, it does terrible things, horrible things. Okay. So, what I was trying to ask was, does the tuple have to have one element from every set in the relation, or set in the collection? Yes. Yes. A two-place relation, R, on the sets S and T is called a binary relation. Binary relations are the most common ones that we'll deal with. Aside, well, predicates are also quite common, but, you know, where we have a predicate, we will refer to it as a predicate and not a relation. And where we have a binary relation, we will refer to it as a relation. So it looks like we have mostly binary relations, but if you count the predicates as being relations too, then there you go. So we will often write SRT instead of the more proper S, T in R. When we have a binary relation on the elements of the same set U, we say that R is a binary relation on U. So this is introducing the concept of having a relation, having a set, and having a relation relate things from that set to the same set again, which is most of the time, especially when we're dealing with things like, you know, the natural numbers. Hey, Mark's figured out how to do these Unicode symbols. You could probably just copy and paste from the slides into the chat, and that would probably work, right? Yeah. So, although ARBRC, I'm not sure we're ever going to use that. I'm not sure we're ever going to use this notation. This notation here. I'm not sure we're ever going to use it to mean that. So, to be completely honest, it's going to be like unary and binary relations most of the time. So, yeah. Anyway. Oh, yeah, and, you also have the operator problem. But anyway. So, relation properties. These are properties of relations. The domain of a relation R, subset of ST, S times T, is written dom R. That would be domain, not dominatrix. The domain of R is the set, although both of those have the same root word in Latin, I think. The domain of R is the set of all elements S of the set S, such that S, comma T is in R for some T. So basically, if you think, oh, cool. Yeah. If you think of the domain in the same way that you would have learned domain for mathematical functions in high school, like, f of x, it's the same idea, right? The domain is x and the range is y, right? Same thing applies here. All of the s's that are in this are the domain, and all of the t's that are in this relation are the codomain, or the range. Codomain sounds a bit nicer, though, so yeah. Yes, cool. Yes, and functions. If a relation R subset of S times T has the following property, it is a partial function. So, if S, comma T1 is in R, and S, comma T2 is in R, that implies that T1 is equal to T2. So, that is to say, if you are starting from one S and going to two T's, it's a partial function if those two T's are the same T. Again, we're gonna be dealing primarily with binary relations, but yeah, I guess you would have like for the codomain, if you had like a triple, like a relation on 3 sets, it would be like domain, codomain A, codomain B, or it just depends on how you want to define it, really. Is domain and range just for binary relations? What if you have a ternary relation? My instinct would be to say like codomain of T or codomain of U or codomain of whatever. Yeah. So, here we go. So, partial functions. So what in effect that means is that each element of the domain is related to at most one element of the codomain. If S is in the set S, if S in the set S is also in the domain of R, we say that S is defined on R. We write this as S down arrow. Otherwise, we say that S is undefined on R, and write this S up. So this is really just a predicate on membership in the domain. If, in addition, the domain of R is equal to S, that is, if every element of S is in the domain of R, then R is a total function. So it has the secondary property of totality. Supposing that we have a binary relation R on S and a predicate P on S, we say that P is preserved on R if P at S and R SRT implies P of T. So if the predicate is transferred through the relation, then we say that P is preserved on R. A relation is just a set of tuples. We ask, is the tuple in that set? And it returns true or false. We really need to ignore the is related to T through R definition as we get to more entities. Yes. So, yeah, like... Yeah. As I said previously, while it's important to know that relations can have as many sets they relate to as you want, most of the time we're going to be dealing with binary relations, and we will probably not venture much further than ternary ones. So there you go. Functions. So, are there any questions so far? Anybody got any questions so far? Give me a thumbs up if you're all good so far. Maybe I'll even do a poll. Like, I'm assuming this is all... Is this, like, review so far? Okay. I don't 100% understand what a predicate is. Is there a simplified definition? Yeah, the simple way of thinking of a predicate is that it's a function which relates the elements of a set to a true or false value. We have a slightly more complicated version, right? But the essence of a predicate is like... I'll make a concrete example. I'll make a concrete example of it. Let's say our set is the days of the month, and your predicate is, did it rain that day? You can slot one of your days of the month into the predicate, did it rain that day? And you'll get either yes or no. That's what a predicate is. So, cross product, yeah, that's what it's called. So, going back to this guy, you take every element in S, and you make a tuple with each element in T with it. You take every element in... you take this element, you make a tuple with each one of these. You take this element, you make a tuple with each one of these. So... Yeah, so... I'm trying to think of a good analogy for cross product. Oh, I got it. Yeah, binomial expansion. Binomial expansion is an example of it. So if you have like x plus 1 times x plus 4, right? The way that you expand this is the same way that you get the cross product of two sets, right? It's like this guy times that guy. It's just, you know, in the case of sets, you're making a tuple rather than like actual multiplication, right? You know, x, that guy, there we go, plus 4x plus 4, right? Each one of these is, you know, each one of these is, you combine the terms in the same way that you do for cross multiplication or cross product. So there you go. And then, of course, if you were doing things algebraically, you would collect the terms, but we're not, so we don't care. Partial versus total, yes. Does it include the empty set? I don't... Yeah. No. No, it doesn't. I don't... It's difficult making assertions like that, but there's no such thing as an empty tuple, I don't think. Tuples have to have elements. So, one more time, partial versus total function. So you take a relation. If you add one property, add one property, you get a partial function out of a relation. And if you add one more property, you get a total function out of a relation. So, to make a partial function, you need a relation such that whichever s you start with, it only maps to one t, right? If s maps to multiple, like if you have multiple tuples, right? That means that the t's are the same in both of them. That makes it a partial function. That, oh, I forget what it's called. It's, oh, come on. It's not idempotency. Injective, surjective. It's, one of those. Surjective? Let's see. In mathematics, a surjective function is a function f that maps every element of x to every... yeah, no, that's not quite it. Injective, surjective, one of these guys. Injective, surjective, bijective. Yes! Okay. So. Yeah. Yeah, okay. So this is a good site. So to get something to be a function in the first place, you can't have multiple arrows going from the A set to the B set, even if the A set and the B set are the same set. So, you know, for example, if... okay, example on the integers. Negation turns a negative integer into a positive integer and vice versa, right? So if you applied the negation relation to 5 and you got either -5 or -13, then it's not a function. That's not a function, right? In order to be a function, it has to go from 5 to -5 and no other place. Okay? Yeah. So, it's isomorphism is, iso meaning the same and morphism meaning shape. So, like, that means there are two things that, like, look the same. I don't know. It's not equivalency. Isomorphism is not equivalency. I would have to look up the definition. Anyway, so that's a partial function. To make it a total function, you need one more thing. You need to add the property that every element in A has some B that it relates to. That, like, different A's can relate to the same B. That's allowed. But each element of A must be related to some element of B somehow. There you go. Good. I'm glad I asked. Okay, cool. Let's see. Yep. Good. So, so let's get on to some more math. Good. Let's talk about binary relations. For most of you, this is a review, and that's good. Binary, so 1 over x is partial, but x is total. Yeah, because x isn't, like, it's not defined for x equals 0, right? So if the carrier set were the real numbers, then yeah, x is a partial, 1 over x is a partial function. If you're discounting the existence of infinities. I don't know. That one's a little bit of an edge case, but but yeah, if you start thinking about, like, piecewise functions and that sort of thing. Yeah. So, anyway. binary relations on properties. Now that we have some relations, we can start making assumptions about them, or asserting properties of them. So you'll probably have heard of most of these before, but they're very, very important for establishing things like orderings. This is the section on ordered sets, and these properties, in the same way that in the same way that we required properties to turn a relation into a function, we will require properties to turn a relation into an ordering. Calc check. Oh my god. You guys in your calc check. My goodness. Okay, so number 1, reflexivity. If a relation R relates every element of S back to itself, it doesn't have to only relate every element of R back to itself, but it needs to minimally relate every element, every element of S back to itself. So, something like a multiply by 1 operation is reflexive. Symmetry. If the inverse of every tuple in R is also in R. Oh, oh, no, that's fine. I thought I needed brackets there, but I didn't actually. I was pretty careful with these slides not to get any, like, typos in the formulas, because that would just be deadly, you know? So, S comma T, for all S and T in the set S, SRT implies TRS. So, if you have ST in the relation, that implies that TS is also in the relation. Right? So, actually, negation would be an excellent example of a symmetric relation, because 5 becomes -5, and negative 5 becomes 5. There you go. That's symmetry. Antisymmetry: if there are no tuples in R satisfying the above property unless S is equal to T. So, trying to think of an antisymmetric relation. Like, okay, antisymmetric relation. Let's say we have S as the set of human beings, the set of people, and T as the set of hats. And R is ownership. So a person can own a hat, but a hat cannot own a person. Right? But yeah. Yeah, once we get into, like, the ordering that you regularly understand to be the case over the natural numbers or over the integers, some of these are, going to become more clear. But, I want to... Give me this. Let me try to come up with analogies. So, transitivity. If a relation exhibits the transitive property... Ooh, question. Is S equal to T a relation? Yes. So, S equals T would be an equivalence over S and T. And an equivalence is a relation that is reflexive, symmetric, transitive, and total. So, transitivity. Hopefully, you guys did you did transitivity in your intro logic courses. So transitivity is if A implies B and B implies C, then A implies C. right? That's the transitive property. If we apply this to relations, it becomes S, if S is related, if, you know what, guys, I'm going to say maps to for relations, for, like, general relations. I know we haven't defined them as mappings, but, like, I feel like it's a more intuitive way to say it. So, if S maps to T and T maps to U, then S maps to U. That's transitivity. So, here we go. If a relation R on S is reflexive, transitive, and symmetric, so total isn't a condition. Reflexive, transitive, and symmetric, the relation is called an equivalence. So, reflexivity, transitivity, and symmetry mean basically you're just testing. You have a relation for testing if an element, like if two elements in a set are the same element. The reflexive closure of a relation R is the smallest reflexive relation R prime such that R is a subset of R prime. So, what that means, essentially, is that you take all of the elements in R, you add those elements, which would give R the property of reflexivity, and that's R prime. That's your reflexive closure. We will denote it normally. Well, actually, no. We'll use prime for a lot of stuff. It doesn't have a particular meaning except a different set. A slightly different set from the one we're operating on. Similarly, the transitive closure of R is the smallest transitive relation R+, such that R is a subset of R+. In the same way that you take R and you add those tuples that make it transitive to make R+, and R+ is the smallest such set. With reflexive, you do the same thing for transitive, and it becomes the transitive closure. The reflexive and transitive closure of R is the smallest reflexive and transitive relation such that R is a subset of R star. Another way to think of a closure is as the set of all tuples that would need to be added to R to satisfy the given property. So, you should think of, like, closures as a general, like, I was about to say set. Closures are a type of operation you can perform on relations. You can find the closure with respect to any property, not just reflexivity or transitivity. Like, you could find the symmetric closure. You could find the anti-symmetric closure. You could find, the closure that makes the thing total. All of these types of things. Any questions there? So let's talk about pre-orders and partial orders then. If a binary relation R on S is both transitive and reflexive, we call it a pre-order. So pre-orders are well, anyway, I'll give you the description, and then I'll give you, like, my way that you might have of visualizing it. So we will either use S less than or equal T, or S square less than equal T to indicate a pre-order. So when we're talking about, like, pre-orders or partial orders or total orders, we are generally going to use the angle, like the angle one, but sometimes the square one will show up too. I've got a question, which I'm going to answer now. Yes. Could tuples be removed to make a closure? No. No, you have, like, R prime has to be a superset. So no, you can't remove anything from R to get to R prime. You have to add stuff. Still don't get closure. Okay. Well, we all need closure. Okay. So let me think. it'd be fine to do it, I think, like we could do a small numerical example. So let's say we had S is equal to 1, 2, 3, right? And we had R, which had in it 1, 1, and 2, 2, right? R prime, which is the reflexive closure, would be these guys union the third one, 3, 3, by like this tuple 3, 3, which does not appear in R. When you add it to R, it makes the relation reflexive. So this means that R is the reflexive closure. It closes the property. It completes the property of reflexivity. So that's what a closure is. Hopefully that's understandable. Yeah. So, yes. So generally we'll use less than equals or greater than equals, but if we use it without the line underneath the symbol, then that means essentially that is implicitly meaning S is less than T and S does not equal T. So R itself was not a reflexive relation. Yeah, remember the definition. For all S in T, S are S, right? So it's not reflexive unless every element of S is related to itself, right? If you just have some elements of S related to itself, that's, it's like good for you, but it's not reflexive. It's only reflexive if the for all is satisfied. So R itself wasn't a reflexive relation, but we add the least tuple to make it. Yes. Let's say R had 3, 1. Would that be removed from the reflexive closure? Good question. So let's see. Let's say we had let's say we had 3, 1 in here. Sure. The reflexive closure would be the same thing, but with 3, 1 in it as well. So R has to be a superset of R prime has to be a superset of R. So you're not allowed to remove anything from R. We're not looking for okay. So the condition is for all S in the set S are S are this is true. S are S, right? S comma S must be in the relation. That does not mean that the relation must be exclusively composed of things which are reflexive, right? Otherwise, it would be impossible to have a reflexive and transitive closure, right? So in order to satisfy the transitivity property, you have to have tuples in there that aren't mapping elements of S to itself, right? You have to have elements that are relating S to other things that are in S, which, those do not contribute to the set. They do not contribute to the relation being transitive. So you're allowed to have extra junk in there, basically. You're allowed to have extra junk. So if you take the set, here you go. Take the set, take the union out, right? Take this set. Is it reflexive? How about 1? Is 1 R1 in here? Yes. How about 2? Is 2 R2 in here? Yes. What about 3? Is 3 R3 in there? Yes. Then it's reflexive. Period. Cool. Looks like people... Yeah. Okay. Looks like people have got the idea. This is good, right? Um, like, I kind of... When I was putting the slides together, I was kind of... Oh, hey, look, we're over time now. Whoops. We're out of time, folks. When I was putting these slides together, I was kind of like, the textbook doesn't even suggest reading chapter 2. This is based on chapter 2 in the textbook. The textbook's like, only review this if you're like super new to this, and if you don't know any of this, don't ask me. I've got some references. But yeah, so yeah. I remember from the prof from 2FA3 indicating this wasn't the case for some reason. Well, as much as I am a poor humble sessional, and I can't really speak to Dr. Farmer or his class, but yeah, how can you have something that's both transitive and reflexive if only tuples of the form s comma s are permitted? You can't. It's a logical inconsistency. Here's a question. But 1, 1, 2, 2, that set would not be a reflexive closure because it is not the minimal set. Good point. Good clarification. So if you added something here that did not contribute to the reflexivity property, then no, it's not the reflexive closure, because we've defined the reflexive closure as the smallest relation such that it satisfies the reflexivity property. That means you're not allowed to include junk on this side, regardless of whether any junk exists on that side. That might actually be the source of the confusion that we were having. Cool. We've been taught this before, but never memorably. Well, I hope that we have a good math class. Part of the problem with a very experienced prof is they think so naturally in this kind of stuff. It's like, of course this is the case. It doesn't need explanation. Whereas me, I'm here's a little bit of a secret about me. I'm a B student, or at least I was during my undergrad. I was a B student, so nothing comes naturally to me. I have to struggle for everything. So that means I appreciate a little bit more your struggle. Because I'm not that bright. Okay. Yeah. What does an anti-symmetry pre-order become? Partial order, I think. Let me just pull it up. But we'll talk about this next time. Yeah, a pre-order which is also anti-symmetric is a partial order. We'll talk about pre-orders and partial orders next time. Yeah? I think that's enough for today. I mean, I kind of feel like you have to have okay. So the comment is, thank you for giving me an example. Every prof before has refused an actual example. That's well, I can't really it's against my code of ethics to say anything about any other prof who's teaching anything. I can only tell you that my own personal philosophy is that examples help, and you know, as a professor, I would hope that I would be able to produce an example for you on the fly if you needed one, because that's an indication of my own knowledge of the material. And if I don't know the material, how the heck are you guys going to know the material? So I always, you know, when I need to give an example, I give an example. But yeah, no, this is. I hope we learned something today. Yeah, cool. All right, I like you guys. You guys are cool. I like this class. I like teaching a third year class. This is fun. Okay, so I'll stay on the line a little bit more. Is there a tutorial this week? Well, considering it's Friday, no, the tutorials start next week. They've got the TAs are planning a LaTeX extravaganza for you next week in tutorial. So yeah. Hey, you're a TA. You get privileges. Ta-da! There we go. Cool. All right. Take her easy, folks. Have a nice weekend. Yep, all that good stuff. Don't do anything I wouldn't do. Next class, we're going to finish off ordered sets. We're going to talk about induction, and that's probably going to round us out. So, yeah. Yes. Take her easy, folks.